Hello, lovely people. This is our second lesson in our unit on forces and momentum. So previously, we got an introduction to what force is, how it generally affects objects, and the different types of forces that exist. And we practiced identifying all the different forces that might be acting on an object in a particular situation. Our goal today is to really take all those different forces in a particular scenario and start to consolidate them and figure out, okay, if we've got multiple forces all acting on an object, what's the overall effect? So we'll start trying to consolidate into this idea of net force, as well as start making the connection between force and motion. So let's dive in. So first idea that I want to talk about here is something called inertia. And in this video that you see right here, you can see inertia in action. We've got a person jumping on a trampoline, and there is a pile of chalk powder, chalk dust, right there where the person is jumping into, and we can see the inertia of the chalk dust in action right here. So based on this demonstration, what do you think inertia is? So our basic idea of inertia is that inertia is this property that objects have that they try to resist changes in motion. They try to avoid accelerating, right? Basically, this is sort of us saying that, like, we are not alone in this universe and being lazy. Pretty much everything is kind of lazy and grumpy and wants to be left alone and just allowed to keep doing its thing, okay? So, so what this means is that objects that are at rest tend to stay at rest, all right? So if something's not moving, it wants to keep not moving. Kind of like you in the morning when your alarm goes off and you're like, no thank you, I would rather stay right here. That's inertia. That's inertia. It's physics. That's all it is, okay? So objects that are at rest tend to stay at rest, and objects that are moving tend to maintain a constant velocity. So they tend to keep moving in the same direction, at the same speed, don't want to speed up, don't want to slow down, no thank you, just like let me keep doing my thing. All right, so this is the idea behind inertia, is that things try to avoid changes in motion, avoid acceleration. They kind of want to just keep maintaining the same velocity that they've already had. Thank you very much. All right. So my next question then is, given that all objects, all matter in the universe has this tendency, this property of inertia, but some objects have more inertia than others. What factor determines how much inertia an object has? Well, we might be tempted to think that maybe inertia is based on like momentum or velocity or some element of the motion. But the thing is, what we see here from this definition is that objects will have inertia whether they're moving or whether they're not moving. Things will still have inertia. So inertia can't really depend on the motion of an object. So if we think about the amount of inertia something has, how hard it would be to get an object to speed up or slow down or start moving or whatever, really the biggest factor that comes into play is the mass of our object. And that's really our one defining feature, our one determinant of the amount of inertia that something has. So what that really means then is that we can kind of define mass in two different ways. We can think of mass as how much stuff, how much matter makes up an object, and that's probably the definition that you've heard before. And that's a good definition of mass, to be sure. The amount of matter in something, beautiful, yes. But another way we can think then of mass is it's a measure of how much inertia an object has. So the more stuff makes up an object, the harder it is to accelerate that object, the more it has this tendency to maintain a constant velocity. Okay, and we can see that in the animation right here, that if you decide to headbutt an elephant, don't headbutt an elephant, because the elephant has much more inertia than you do because it has much more mass, all right? So you are going to be on the losing end of that interaction. So, you know, if you come across an elephant, maybe don't run into it. Do appreciate the helmet, though. I'm sure that helps. Right? And as a reminder, mass for our purposes in physics is going to be measured in kilograms. So kilograms are our default unit for mass. Maybe in some other classes, grams are sort of your default, and that's understandable, but we tend not to be dealing with like super small amounts of things. We're talking about like everyday objects, which it's usually easier to use kilograms for. Okay. So then this brings us to Newton's first law of motion, which is also the law of inertia because it basically kind of just gets at the same idea of inertia, okay? And this law states that if the net force on an object is 0, all right, which basically just means then that like all of our forces are balanced, there's no stronger force in one direction than in another, all of our forces are canceling out, then our object is in a state that we call equilibrium, all right? Equilibrium being the forces in all directions are equaled out, they balance out, all right? And if an object is in equilibrium, it's going to maintain a constant velocity and a constant momentum, all right? And so basically the idea behind this is that if there's not a net force on an object, it's just going to stick with inertia, all right? It's just going to keep doing the thing that it was already doing. Now I shared these videos because they're cool, but also just want to clarify, I'm not saying that in these situations the net force on the object is 0, but just that that at one point maybe the net force was 0, and so we're seeing the inertia still carrying on and causing our objects to maintain the same velocity that they were at until that imbalance in forces really gets acceleration going for our objects. Okay, so we can see that previously the net force on the water was 0 while the balloon was still intact, and so it was just sitting there. And so once the balloon disappears, we're starting from a state of rest for our water, and it's going to take a measurable, small but measurable amount of time for gravity to really be accelerating that water and getting it to move and stuff like that. And similarly for our apple, potentially it had a constant velocity because it had 0 net force acting on it, and so we see that tendency to keep moving until our forces change and then things start to accelerate it. All right. So then, getting at this idea then of multiple forces and net force, let's really start to dig into that idea now, okay? So let's consider this scenario. We've got a 15-kilogram object. It's hanging from a rope, and the rope is exerting 140 newtons of tension force on this object. So let's start by drawing a free body diagram, and that's pretty much always going to be our first step in this unit, is let's draw a picture, figure out what all the forces are that are acting on this object. So I'll go ahead and just draw a shape and go ahead and put in that it's a 15-kilogram object, so it's helpful to just keep track of that in my picture as well. Now, I am told in this problem statement that the rope is exerting 140 newtons of tension force on the object, and so it's holding it up. The rope is exerting an upward tension force of 140 newtons. But that's not the only force that's acting on our object. We are going to go ahead and make the grand leap to assume that this is happening on Earth, because usually the stuff that we're looking at is happening on Earth. And so there is also a downward gravitational force acting on this object. So then the question is, what is that gravitational force acting on our object? And as a reminder, here on Earth, the acceleration due to gravity is 9.8 meters per second squared. So given that and the information we have, what is the gravitational force acting on this object? Well, I can calculate gravitational force, aka weight, those are the same things, gravitational force and weight, using our equation Fg equals mg, where Fg is the weight or gravitational force acting on the object. I know that the object's mass is 15 kilograms, and since, again, I'm assuming that this is happening on Earth, I can assume that the gravitational acceleration for this object is 9.8 meters per second squared. That's how fast it would be accelerating if it were just in free fall, okay? And so I can multiply those together, and I determine that there is a grand total gravitational force acting on this object of 147 newtons. So given that information, is our object in equilibrium? If so, how do you know? And if not, which way is our object going to accelerate? So I can tell that this object is not in equilibrium, because equilibrium would mean that both forces were canceling each other out, that we have equal pulls on both sides of this object. And that's not the case. We have 140 newtons upward and 147 newtons downward. So there's a bigger force pulling down on the object then pulling upward on the object, which leads me to believe then that this object is going to be accelerating downward in the direction of that bigger force. So we're not all balanced out here. We're not in a state of equilibrium. And so our object's not going to maintain a constant velocity. It's going to accelerate in the direction of that bigger pull. So this then brings us to the idea of net force, okay? So if we have multiple forces that are all acting on an object at the same time, we can kind of put all of them together and sort of sum them up into one number, which we call net force. And net force, which we represent as F with a little subscript net, for net force, all right, just describes like what is the overall unbalanced force on our object. So like if we look at all of our forces, how much of our force gets canceled out, and then what's left over at the end of it. So if we jump back really quickly to our previous scenario with this 15 kilogram object that's hanging from a rope, if we were to look at this, we would say, okay, there's 140 newtons upward and 147 newtons downward, all right? So basically all 140 newtons upward is getting canceled out, plus there's another 7 newtons left over. That's sort of our difference, that part of the force that is unbalanced, that doesn't get canceled out. So the net force in this scenario would be 7 newtons downward, because that's the amount of force that isn't getting balanced out and isn't getting canceled out in this scenario. All right. So then in order to calculate net force, we just saw an example that was nice and gentle and easy. If we just have 2 opposing forces, we can just subtract, that's fine. But sometimes things may get a little bit more complex, so let's just walk through step by step how we're going to calculate net force in those situations. The good news is you've done this before, because you're going to see this process for calculating net force is exactly the same as how we calculated overall displacement in our previous unit, okay? Because displacement and force are both vectors. And so if we're finding their combined effect, we can kind of approach it the same way for both of them, okay? So first thing that I recommend doing is drawing a picture just to kind of organize which way everything's going. Again, we call that a free body diagram, or FBD, when we're talking about force vectors. And then we'll want to break it down into our different dimensions, okay? So we'll start with all of our horizontal forces, find the overall combined effect of those horizontal forces by adding up all your forces to the right and subtracting all of your forces to the left, or vice versa. But we're ultimately just trying to figure out what's unbalanced in our horizontal direction, and then repeat that process for all of our vertical forces. Add up everything that's going up, and subtract everything that is going down. And then ultimately we will have potentially some unbalanced horizontal force and some unbalanced vertical force. And so if we're trying to find the combined effect of that, something getting pulled both like to the right and upward or something like that, we can find that combined effect using the Pythagorean theorem. So we can think of those 2 component forces in the horizontal and vertical direction as 2 sides of a right triangle, with the overall combined effect being represented by the hypotenuse of that right triangle. So we bust out a little a squared plus b squared equals c squared, and we can find our overall net force. Okay, so let's work through a quick sample problem just to kind of see this in action. So we've got a rubber chicken. And there are 5 kids who are all fighting over this rubber chicken because obviously it is a hot commodity. Okay, so we've got these 5 kids. Alice is pulling the chicken to the east. Bobby's pulling it north. Cindy's pulling it west. Danny's helping Bobby and also pulling it north. Emily's pulling it to the south. Poor rubber chicken. Good thing it's rubber. And also not alive. That also helps. So we want to figure out what is the overall net force acting on this rubber chicken so that we can start to predict, okay, what's it actually going to do? Like, which way is it going to move, and is it going to accelerate? What's going on? Okay, so first thing I want to do is draw that free body diagram. So here's what I put together for that. So we've got our rubber chicken and all 5 forces. So I've drawn them in there in the correct directions with those quantities labeled on it as well, just so I can see like what I am working with here. So here are all of my forces acting on my rubber chicken. The next thing I'm going to do is start combining them, but do it 1 dimension at a time. So I'll start off in the horizontal direction, the east-west direction. I've got 15 newtons to the east, 12 newtons to the west. Those are in opposite directions, so we're gonna subtract those 2. Because they're going to attempt to cancel each other out. So I subtract it and I determine that there is an overall net force to the east of 3 newtons, okay? So these don't quite balance out. I've overall got 3 newtons more going to the east than to the west. So that is my horizontal force that is acting upon my chicken. And then I'm going to repeat that process with our north-south forces as well. So I've got 2 forces that are going to the north, both 10 newtons and 8 newtons. So those are working together. I'm going to add them up and then subtract my 14 newtons that are going to the south because that's in the opposite direction. So if I do that, I get an overall vertical north-south force of 4 newtons to the north that didn't get canceled out in this interaction. All right? So now I've got an overall horizontal force of 3 newtons east and an overall vertical force of 4 newtons to the north. And again, those are perpendicular to each other. So I can go ahead and think of them as the 2 sides of a right triangle, with the hypotenuse then representing the overall net force. And I can calculate that using the Pythagorean theorem. So net force squared is going to be equal to 3 newtons squared plus 4 newtons squared. So that's going to end up being 9 plus 16 gives me 25 is equal to net force squared. And so if I square root both sides, I'll get that the net force is 5 newtons in the northeast direction. So overall, this chicken will be accelerating towards the northeast. So good news for our north and east kids, I guess. All right. So with that, let's go ahead and just check your understanding really quickly. A few problems just to make sure we've solidified these ideas. So first of all, consider we've got a book that's 1/2 kilogram sitting on a table, just sitting there. All right. What is the net force acting on that book? The book is just sitting there. It is not moving and it is not accelerating, which means that the net force is 0. So presumably we've got a downward gravitational force, an upward normal force from the table, and those must be perfectly canceling each other out for the book to be just sitting there. So net force acting on our book is 0. Let's consider another object. So we've got a 0.2 kilogram hockey puck that is sliding along at a constant velocity of 5 meters per second to the east. What is the net force on this moving puck? We didn't even need to calculate anything for this one because we saw the phrase constant velocity. If our object is moving at a constant velocity and it's not accelerating, that's a sign that it is in equilibrium, and therefore net force is still 0, even though it's moving. Because if there were a net force, it would be accelerating. It's not accelerating, so there's no net force. Everything is balanced out. Whatever forces trying to slow down the puck are balanced out by forces trying to speed up the puck at the same time. So everything's balanced there as well. Good, 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 good. Next one is we consider our object below here. We've got this little object, rectangular object, that has 2 forces acting on it, 5 newtons this way, 3 newtons that way. What is the net force acting on it? The net force acting on it is 2 newtons to the right. I could do that by just subtracting the 2 of them because they are in opposite directions. So 5 newtons to the right minus 3 newtons to the left gives me an overall force of 2 newtons to the right. Last question, starting to connect this over to the motion of the object. So let's imagine that this rectangular object is already moving left by the time that these forces are applied. What will this 2 newtons right of net force do to the movement of the object? So if our object is moving to the left and the net force is pushing it to the right, we've got our velocity and acceleration in opposite directions. Velocity is going left, net force and acceleration are going right, and when those are in opposite directions, I expect that our object is going to slow down, that net force is going to be stealing away velocity and momentum from our object. So it's going to get slower and slower, and maybe eventually it will come to a stop and even turn around and accelerate in the opposite direction, depending on how long we leave this net force acting on our object. That is it. Hopefully you're feeling a little bit better about these ideas of force and net force and really starting to make those connections between the motion of an object and what that tells us about whether our forces are balanced or not. So go forth, do some more physics, go be brilliant.